Hello and welcome to another Topics in Depth session with me, Craig Barton, and Joe Morgan, kindly supported once again by Tez. Now, Joe, what's going on here? Because I'm seeing that we're doing angles in depth, and I thought we'd already done angles, so what's happening?
Oh, last time we did angles and parallel lines, which was a very specific part of angles, because the whole idea here is that we don't take entire topics in one go, and we look at little bits of topics.
In depth, some
In depth, yeah. So last time we did angles and parallel lines, which was actually the sort of later bit. Today we're doing angle basics.
Okay.
So this is the stuff that's covered in primary school and say year 7, kind of the beginning of angles, like angles on a straight line, angles and triangles, measuring angles,
Okay.
all the kind of stuff that leads into angles and parallel lines.
Now, I'm already sensing this might be some of the stuff that I might have glossed over in the past, but we're going deep here.
Yeah, I guess the idea is that, and I told you the story last time about the colleague I had who kind of taught all this stuff in 2 lessons.
That's right, yeah. That's angles from start to finish.
That didn't include angles and parallel lines, but it was all of angles from the concept of an angle right through to those complex angle problems that involve straight lines and triangles and vertical opposite angles, did the whole lot in 2 lessons. And my argument was we need to know this topic in depth, and we need to plan to teach it in depth, and we need to make sure our students know it not at a superficial level, so that they can then use it when they go on to angles and parallel lines, circle theorems and all the things that follow. So they need to really know these fundamentals.
You've sold me on the dream, Joe. All right, let's go for angles in depth.
Right, now, do you remember last time I said that whenever you teach any topic, you need to think about a few things when you're planning it. This is the same for any topic, but let's say for angles, you need to think about what is on the curriculum and where does the topic come from and where does it go to. So we're going to talk about what's covered in primary and where it ends up in secondary.
Nice.
You need to think about how you're going to assess the students before, during and after the teaching, and what their misconceptions will be, which is the really interesting stuff. We love talking about misconceptions. What activities we're going to use, what resources, and then how we're going to achieve that kind of level of greater depth. So how we're going to make sure that they actually really understand this and not this kind of, like I say, superficial kind of rushing through it kind of level that a lot of my teaching has done in the past.
Me too. And we'll say for the benefit of whether you're watching this or listening to this on the podcast, the PowerPoint that we're using will be available to download either from Joe's blog or on the podcast show notes page. You'll be able to get it, so don't worry about if you've seen some cracking resources here, you're thinking, I want a piece of that. It's coming your way.
Yes, and underneath each slide in the notes section is the link to where I got the resource from, so it's all easy to access.
That is organised, Joe. That is organised. Okay, here we go.
Right, so primary, it starts surprisingly young. So my daughter is currently in year 3 and she has already done some angle work. I mean, shape and space is a big thing at primary school, and in fact, currently controversially being moved off the early years curriculum, but at the moment it's there from a very young age, so year 2 being kind of 6-7 year olds, you know, and they might kind of do the kind of robot thing of a quarter turn, and they might be able to turn their body and that kind of thing. So this idea of understanding a quarter turn, a half turn, a 3/4 turn is done very young, and it's done not in the kind of way that we'd see it in secondary school, but in this, like I say, kind of turning robots and that kind of thing.
But it's a good start, that, right?
It's exactly what's needed. I mean, they've got the hard job in primary because they're teaching the concept of an angle.
Yes.
So they have to really understand the idea of it's nothing to do with a distance between 2 lines. It's to do with a measure of turn, and that's tricky.
I mean, I've said this before. You could not teach me. You could not pay me to teach primary.
Oh no,
like the
it's so
concept of
complicated.
No, I'm all right.
It's the really, so they have the hard job. They deal with all the real fundamental stuff, and then as long as if we get students who understand the idea of an angle, they've done the hard stuff for us, and we can just teach them, you know, the nice easy angle facts and the circle theorems and all that stuff. But that idea of what an angle is, that's the tricky bit.
Yes.
And they start that very young, rightly so. And then in year 3, they're doing. They're starting to see those words acute and obtuse. And it's always interesting where you see a teacher in year 7 spend a long time on acute and obtuse. They've done it since year 3.
Wow.
In fact, most students, I can't say all students, but most students in year 7 don't need us to spend a long time on that because they have done that for years.
Yes.
That's the one thing, acute and obtuse, that you can just kind of rely that they've done lots of that in primary school.
Okay.
By year 4, they're looking at types of triangle, they're looking at types of quadrilateral.
Wow.
They're ordering angles by size.
Yes.
And at that point, we can talk about some misconceptions. Okay. I mean, this idea of angles being different sizes and which angle's bigger and which one's smaller. Have a look at this picture. So saying that angle A there is smaller when we can see it's the same as angle B. And
classic.
You can see where that misconception's come from.
And particularly if they're thinking bigger and smaller, they're just meeting that in terms of lengths of lines and stuff.
Yeah.
And it goes back to what you were saying, the whole concept of an angle. What a weird thing to get your head around.
It is. It's you can understand the confusion here, and you know it seems so obvious to us, and it's that whole curse of knowledge, where to us it's like, of course we can see they're the same size.
Yes.
But actually I can totally understand why a child would not see
100%.
that. Another one there, angle A is larger, and that's because the arc is larger, or you know, it's just been, you know, so they are actually the same length lines and the same size angle, but the arc has been drawn larger. Angle A there is the only right angle. Well, actually, they're all right angles.
Yeah.
And again, a common misconception, and we know that this comes from students just seeing examples presented to them in the same orientation, or with the same length.
That sneaks into so much stuff, doesn't it? The standard conventional presentation, whether it's shape stuff, whether it's number stuff, and it's these kind of boundary examples or non-conventional examples.
The classic example is always the hexagon, isn't it? Where you sort of show your students, they're so used to seeing a regular hexagon, that show them any six-sided shape, and they won't use a hexagon if it doesn't look like a regular hexagon.
Or your upside down triangle and all that kind of stuff. Classics.
And there's another one. Triangle A has the bigger angles. Oh, sorry, triangle B has the bigger angles because it's a bigger triangle. And that actually comes back when we do similar shapes, which we might do in year 9 or year 10, and we talk about the scale factor is 2, and all the lengths have been increased by a scale factor 2, but the angles haven't been increased because of course they can't. So all of this comes down to, like you say, showing those boundary examples, not showing, you know, just thinking carefully about the examples we show.
And I always think, again, I've rethought this recently. Like, I want to be hitting kids with this stuff as soon as possible. I don't want them having this narrow conception that right angles are always horizontal and vertical, and I want to expose them to this stuff early on, so it becomes just normal. It doesn't. These shouldn't be the weird examples. These should just be.
They should be all over the place.
Examples.
Yeah. This is very, you can tell by the font here. This is from 1978. So some research.
You love that. I mean, that's quite modern for you.
That is, yeah. But this is interesting because someone's done some research into misconceptions in angles.
Okay.
And they were asked to. There's 5 options here, and they're asked to circle the largest angle.
Wow. Okay.
I wonder if you can guess. So we can see that the largest angle is angle 3, and that is the most common answer.
Okay.
But I wonder if you can guess what the sort of misconception is.
Well, already I'm getting the legal team onto you, because are you doing like a guess the misconception rip-off or something like this? So the viewers all.
Well, I know it works well because it works well when you do it. So yes, I'm testing you. This is your own game that I'm asking you to play.
And for the benefit of viewers here, I've not seen these. I've done zero prep for this session. It will become very apparent. Wow, I'm torn between 2 and 4.
Right. Yep.
If I had to say, I'd go 2.
Okay, so amongst 11-year-olds, 4 was the most common, and amongst 15-year-olds, 2 was the most common. So you're absolutely right.
Wow, and I love it when misconceptions switch over time. So say that to me one more time. Which way around?
So 11-year-olds, 4 is the most common misconception. So they think that's a big angle with the very long legs. And then the 15-year-olds think that 2 is the largest angle with the big arc. But actually, in both age groups, the majority did answer 3.
Yes.
And these are 11-year-olds. These aren't primary school children. So these are children where they have spent a number of years looking at measures of turn. And so most of them, in fact, I've got the stats there. I know it's a bit small, but it says 53% of the 11-year-olds got it correct, and 77% of the 15-year-olds got it correct.
Now, this is fascinating. And whilst we're here, just the kind of pedagogical points, and you've nicked my idea. One thing I love to do, John, I'm sure you'll back me on this, is it's a great thing if you show that exact same exercise to kids and say, what's the right answer? So we'll get that established. And then, what do you think the most popular wrong answer is? And then say to kids, say that you were sat next to somebody who was convinced that 2 is the largest angle. How would you convince them that it's not right? How would you convince them that 4 is wrong? And it just means that the kids can experience this kind of deep thought and thinking. I'm obsessed with misconceptions, turning them into a real positive kind of learning thing. That's lovely, that, Joe.
Yeah,
I mean, you could have improved the font a bit there. It's all right. Go on.
1978. Now, there's a lot of text here, but if I just summarise it, this is William and Shuard, 1994, did some research into learning angles, and they've categorised angles in 2 ways. You've got static or dynamic. Okay. So they're saying that these are different experiences of angles that children need to come across in primary school or in secondary school.
Right.
So it's static would be an angle that is the shape of a corner. So I have an angle in the corner of the table. Yeah, this is a static angle. I have an angle in the corner of my paper. It can be sharp, an acute angle. It can be blunt, an obtuse angle. It can be right angled. But these are types of static angles.
Okay.
Dynamic is to do with movement. So as you open a book, the angle changes. And this actually, when I looked at this, I thought, well, I can't really think of opportunities to put dynamic angles into my teaching other than through dynamic software.
Yes, bit of GeoGebra or something.
Exactly. And we'll look at some examples like that. But I do think that everything we do is about static angles.
Yes.
And it's actually quite hard. I try to then find some activities, and I thought, are they static, are they dynamic? And really, I can't find much to do with dynamic angles. I talked to some primary school teachers about this when I presented this at a primary conference, and they agreed that it's not like I'm missing something. That apart from the kind of turning robot and stuff like that, where you could argue that that's a kind of dynamic experience, really we're looking at angles in a very static way.
And it's a good point now, because if we go to kind of principles of variation, the dynamic is so important because then kids are witnessing change and seeing the impact it's having. That's a good point.
I'll show you some activities. This is a static activity.
Okay.
Children make their own right angle tester, so maybe they just fold a piece of paper, it's got a right angle, and then they take, say, a set of, this is from STEM Centre, they take a set of shapes like that, and they figure out which ones have right angles. This is for, say, year 2 or year 3, and they're trying to understand the idea of right angle by finding shapes with right angle.
And you've got the nice non-conventional ones in there as well. Nice.
Now
I like that.
it's an active learning experience in that they're kind of they're doing something active, but they're static angles. These are corners. And even if you were to make it these angle eaters, which are the same thing, they're little Pac-Mans, but they're basically got a right angle mouth, and then you can get the angle eaters to kind of go around looking for right angles, and it's helping them understand the idea of a right angle, but they are still static angles.
Okay, yeah.
This is Colin Foster. This is so lovely.
He's good, Colin, isn't he?
He is. Look, Colin Foster writes these fantastic sets of activities for every topic. Instant maths ideas.
Yes.
Just from that. Have a look at this. It's really nice. Can a triangle have an obtuse angle?
Yes.
2 obtuse angles.
No.
No, because if you had, say, 100 and 100, that you
I was getting this wrong. Right angle is not obtuse. Is like
no,
obtuse
it's a different category. So we've got acute, then right, then obtuse.
Okay.
Yeah,
so acute is strictly less than 90.
Yeah.
Obtuse.
So this is a really nice. This is a real, like, you have to think about it.
This is nice.
And even 4 acute angles at the bottom there, we know there's only 3 angles in a triangle, because you could sort of, if you're thinking about numbers at that point, you think, well, I could have 4 numbers that add up to less than 180, but actually.
I mean, I'm fuming that he's got semicolons at the end of 5 and 6, but. Question marks at the end of it. I mean, that's one thing I'd criticise this exercise for.
Okay, I didn't notice that. Yeah, but that's easily.
I mean, that's Colin for you, though. Very careless for that kind of stuff. But the maths is absolutely.
I'll show you another Colin Foster thing. So this is Colin Foster.
Lovely.
And this is actually, I suggest this might be a nice start to year 7. Because when they come in year 7 and you know they've done angles before, you don't want to patronise them by repeating it, but you need to check the basics. This is a lovely activity. So they could draw in each section a triangle that fits the description. So can we draw an acute angled isosceles triangle?
Yes.
And then can we draw an equilateral triangle with obtuse angles? Well, no, of course we can't, because we know an equilateral angle, all the angles are 60. So there are some boxes there that can't be filled.
And getting kids to explain why they can't be filled, that's tough. It's really nice. That.
This is a lovely activity for assessing your year 7s coming in, but also sort of stretching them in a way, because they have to really think about this.
That's lovely.
And it's just I think that's again lovely Colin Foster thing. Notice how it's also static angles. We haven't got any dynamic angles in here.
No, better punctuation on that one as well.
Yes, so we like that. Yeah.
What is this?
This again, not the sort of thing I do, but this is from an American website, and this is a lot of people like using this sort of colourful tape on their desks when they teach angles. And then in this one, they've put the tape all over their desks, and they're getting students to recognise which ones are obtuse, which ones are straight.
Oh, okay.
And bear in mind, I'm still talking about doing stuff at primary school here. And the thing of this is, it's an active thing. They're all up and doing stuff active, but we're still looking at static angles. They're still corners.
Okay.
So I think my point here is that we can say we need to teach children about static angles like corners and dynamic angles like opening books.
Yes.
And we can get them out their seats, but they're still not looking at dynamic angles.
Yeah.
This is static angles.
Yes. Good point. Good point.
This sort of activity, it looks lovely. Yeah, sure. If you've got a class of 8, maybe it's practical. In a class of 30, this will take forever to set up. So not for me, but I know a lot of teachers do this whole tape on the desk thing. There's a dynamic angle thing. It's not even an activity.
Oh, that's nice.
This goes around Twitter a lot. It's a classroom door where you can see the angle it's open at, and you can see if you open it wider, it's a larger angle, and if you have a tiny narrow opening, it's a smaller angle. Now that's the dynamic angle, but that's not an activity. So I can't find any dynamic angle.
That's nice though. That.
But yeah, you see wouldn't it be lovely if we all had these on the floor?
Yes.
It's just, there's not much you can find on dynamic angles.
Unless you're using the software.
Yeah. So we're still in primary school, and they've done all that stuff in year 2, 3, and 4, and now they're on to the stuff that looks more familiar to secondary teachers.
And year 5, kind of 9 and 10-year-olds.
9 and 10-year-olds, they're drawing angles. They're using a protractor.
Okay.
They're measuring. They're estimating. They are understanding the idea of degree. So they're moving on from this idea of that angle is bigger than that angle because I can tell by looking at it, and they're actually putting a number on that angle. So they're measuring it. So that's the big change.
And again, I've spent so much time getting kids to practice measuring angles. Again, with the assumption that they've maybe not done it before, but this is the final 2 years of primary.
Well, yeah, they do it in year 5 and year 6, mainly year 5. I think the thing is that so much packed into primary curriculum. Again, that even schools that are sort of following this sort of mastery approach, they're still not getting enough time on any of this.
Yes.
So when people suggest that we don't need to teach things at secondary that have been taught at primary, I don't agree with that, because I can see with my own eyes that they can't do it.
But we certainly need that awareness.
But we do need to know they've done it before, absolutely. Because when I introduce a topic like this, I'll say, I know you've done this at primary, I'm going to be checking that you understand it, we're going to be looking at it in more detail. So it's just the way you pitch it with the class.
That slight little thing, that makes a big difference to the kids, right?
Yeah, that's it. I mean, I've just done percentages with my year 7s, and I started by saying, I know that you've done percentages, because look, here's an example of a SATs question that you all did last June, and I can actually put up that SATs question, and then I say to them, and I've looked at your SATs results, and I know that quite a few of you didn't get this one quite right, so we're going to be doing this in a bit more detail, and by the end of my couple of weeks, you're all going to be getting this right.
Nice.
And it's that idea of yes, I know you've done it before, and I'm not trying to bore you by doing it again. You will need to do this again, and we're going to be looking at this in a whole load of different ways.
Yeah, going deep.
Yeah, going
topics
deep.
in depth.
Exactly.
Keep on brand. Nice.
Now, year 6 looks a lot like what we do in year 7.
Wow.
Finding missing angles in triangles and quadrilaterals. That includes parallelograms. So they need to know the opposite angles are equal and stuff like that.
And they've met quadrilaterals before, like
they
year
had,
4,
yeah,
so,
they had them
but not gone as deep into.
Yeah, they haven't been
angle
necessarily.
properties
Well, they haven't
and
necessarily known that they add up to 360.
Right. Okay.
Finding missing angles at a point or on a straight line, including vertically opposite in year 6.
That's essentially like GCSE foundation. Kind of,
yes,
right? In year 6,
yeah.
right?
So
Not
basically,
much more.
if we add in the parallel lines, and that's all we really do. I mean, we do parallel lines and we do angles in polygons.
Yes.
And then we go on to circle theorems.
Yeah.
But the basic angle stuff is identical in year 6.
Whew.
Relationships may be expressed algebraically, and I think all that means is a plus b plus c equals 180.
Yeah.
Now they've been introduced to protractors then in year 5, so they should be familiar with this bit of kit.
And it's always the semicircle protractor.
Not necessarily, but I mean,
Where do you stand on? Let's just get this.
I wouldn't go near the full circles.
Yeah, me neither.
I think I once knew a student in a GCSE mock who couldn't answer the question because her big circular one was kind of too big for the page or something. Right. I think they cause more problems.
Both are legit though, like in terms of GCSE and
you're
stuff.
not allowed one with percentages marked in it that you could use to cheat in a pie chart question, but you are allowed a circular protractor. I don't see many students with them anymore.
No,
I think they were trendy for a while.
They were trendy. You can kind of whiz them around. I remember whizzing them around like a frisbee or something, right? If you get good at it.
Yeah, we don't want any of that.
No, of course not. That's their main use. So
the thing is with protractor is if you're teaching it, you might want to use a visualizer.
Yeah.
But I'd say it's a little bit fiddly. They can't really, so you're getting your hands in the way, they can't really see. So actually I think I'd start by using something like this rather than try and show it on a visualizer. I'd have this on the screen.
Just so it's clear.
Yeah, I mean, this is really clear. And then the thing is I might talk about, I might start with showing them things like this and then getting them to practice with pictures rather than an actual protractor at first. So they could practice this is a worksheet. They could do this worksheet without getting a protractor out.
And you just want them to say the size of the angle. Can you just go back one slide there, Jo?
Yeah.
So this is a classic diagnostic question I use with a setup like this.
Yeah.
Is you'll say to kids, you have options A, B, C, and D. So you'll have, what's that, 1, 4?
Yeah, it's not a very nice one, but let's say it's 140 or 40. So there's two options.
Well, let's say it's 142.
Okay, 142.
142.
Yeah.
So then you can have 142.
Yeah.
158. Can you see that one?
158. Yes, I can see that.
Okay.
Yeah.
38 or
yeah.
42.
Amazing. I wouldn't have thought of the other two
And
options.
it's incredible. It splits the crowd. Yeah. It splits the crowd because that captures the ones who are thinking, well, it's if you just had 140 or 40, they look at that and think, well, it's obtuse, so it's got to be 140. But as soon as you introduce 142 or 158, then you're really having to think scale and which direction you're coming in.
Now, I have a solution to all of this because I think protractors are terrible things. The way that they're designed.
Are you patented like the Morgan protractor?
Well, it's not my idea, but I'll show you in a second.
Okay, you've hooked me. Right.
Okay, so let's say we're getting into practice without actual protractors. At this point, I'd want some reflex angles in there too. I mean, there's a big gap in teaching how to measure a reflex.
But just
angle.
on this, you're saying here that the danger is that if we rush straight into them measuring it first before they've had a chance, it's almost a bit of atomization, right?
Yeah.
It's before we go straight into the measuring. Yeah. Let's just see if you can. I've measured it, this is the reading, can you read what it's supposed to be? Yeah,
so basically that step before they actually have the physical bit of equipment which introduces, it's like with a pair of compasses where you have the dexterity issues.
Yes.
Right? I mean, it's not quite so hard with a protractor, although I'm sure we've all seen students who can't get the middle bit on the middle, they struggle with the actual kind of, particularly at a young age, that just kind of putting the thing in the right place. And this has a skill without that. So, I'm not saying they shouldn't touch a physical protractor, but maybe they can do this first.
No, I like that.
Because then we can move on to something like this where they are having to get their protractor out.
Yes.
And at this point, there's a couple of things. So if you're doing this in secondary school, then you can say, right, part A, measure the angle with a protractor. And you can say part B, using that answer, what would the reflex angle be? And you could use some letters to that, because the thing is that if you want, you could bring in two skills here. Do they understand how to use a protractor, and do they understand how, once you've worked that out, how you can work out the other angle?
Reflex angles, they mentioned that. When do they come into primary?
That's a good question. I haven't got that on my list. I'm assuming that they're mentioned
alongside the acute.
I had acute and obtuse written down. I didn't have reflex. I don't know. I'd have to check that. That's a good question. So at this point, if you don't want to kind of patronise your students by saying measure the angle with a protractor, you could say, right, part A measure, part B work. Tell me how you'd work out the other one.
Nice.
Now here's the big idea. I saw it in an NECTM document, but it's been around for a while, and the idea is numberless protractors. Which I just think I don't know why we don't use numberless protractors.
Well, I don't know why we. Why would we?
You listed all these 4 options there.
Yeah.
Now, if you look at this one, if I wanted to measure an angle, I would basically just count each little mark is 1 degree. Each big interval is 10 degrees. You can easily count along.
You still go the wrong way. You still.
No, you can't. I'll show you why I think it's a lot clearer. I'll show you in a second a animation which explains it. But just to say, a lot of people, when I talked about this, loved the idea and said, "Oh, but we can't buy them." But someone sent me this where they had printed a load of protractors onto acetate. So like old OHPs. I mean, I don't have acetate lying around, but apparently you can print it, and then it costs 1p per protractor. And they've got their students these are normal protractors, sticking them down onto their work. So they're literally gluing the protractor onto the work. 1p a protractor.
Well, these numberless ones?
No, these are normal ones. But if people are saying, I want to use a numberless one, well, make them out for 1p a protractor. Pretty easy to make them.
But you've got to print acetate.
You've got to print onto acetate. I think that printers print onto acetate. We just need to have the acetate. I believe so, yeah. Anyway, I'll show you a numberless protractor in action. This is from Boss Maths, this GeoGebra. Look, that angle there, I'm trying to measure the pink angle. I can count along. Okay, so I can count that there was 60. Let's say we want to measure, I've put one on the other side here. Let's say I want to measure that. If I start over there, because I can see I'm counting the pink bit, I've got 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. That's 110 degrees. Yeah, there's no number. There's no numbers to confuse me here. There's no numbers to read off incorrectly. I know I want the pink angle there. I'm not going to read it from the other way. Yeah. I don't see how you can make that misconception of going the wrong way in a numberless protractor.
Okay, yeah.
So can you see how there I'm saying I want to measure that pink angle and therefore I'm going to count through. There's no need for those numbers to be written.
Okay, all right. I won't sound fully sold on the numberless one.
I wonder how I can convince you on this.
We've still. So would you just have no numbers? Would you start them with this and then bring in the numbers, or are the numbers?
Yeah. So obviously I don't teach this from the beginning. So if I taught this in primary school, then actually I think it'd be better to have the no numbers.
Okay.
As soon as we go back to one with numbers on, as soon as you've got those numbers, they're not looking at the angle.
Yeah, no,
they're not seeing the pink bit. They're looking at the numbers there and they're reading the numbers off. Whereas here, they are saying, I've been told to measure that pink bit, let's count it.
Okay, yeah, okay.
I mean, I think it's genius, and I don't understand why we have numbers on protractors. Like the double scale thing No wonder it's confusing. So how about no scale? Well, there's a scale, but there's no numbers. It's just so much nicer.
Okay, possibly.
Anyway, this was...
it's beautifully designed.
Well, yeah, I tweeted about it, and then this is Boss Maths who made it in GeoGebra.
I knew this wasn't you. I can tell how much for free.
So I made a GIF. The GIF is of me playing with it.
So the actual file you can just manipulate.
Yeah.
Lovely.
And so you can just basically choose an angle, count it, and then check your answer.
It's got Boss Maths into
you.
You
you
love a bit of Boss Maths.
Yeah.
Nice.
So I love that idea. So anyway, that's everything they do in primary school. They basically do the whole lot.
Yeah.
So let's have a quick look at how it's assessed. I think it's really important for us to know how it looks in Year 6 Stats.
Absolutely.
And this is from the sample assessment.
Okay.
So this was when the government decided to change Stats. Now look at this question. Join dots on the grid to make a quadrilateral that has 3 acute angles.
Wow.
I love it because you're a secondary teacher. You always look at the primary questions and think, well, that's tough. And it's a lovely question, and it's probably not as hard as it looks. I mean, it's the sort of thing that you might want to skip if you're.
Well, I'm skipping it now. I'm hoping you're not going to ask me to do it. That's a great 1 mark as well.
One
Notice
mark.
just the 1 mark.
Everything is at Stats is like 1 mark, really. And that's the sort of thing. And then a bit easier, I think, is this: 5 angles marked. Write the letters of those that are obtuse. So this is standard vocabulary.
And do they have a protractor with them in the SATs?
You know what? I think they must do because there are questions on measuring. Actually, yeah, good question. And then write down the letters of those that are acute.
That's good.
Again, 1 mark each, but just they're used to questions like this.
That's lovely. That.
In fact, I don't think you get this at GCSE.
No, you wouldn't. And if you did, it'd be an absolute disaster. I'll tell you that much.
And then this is a measurement question. Just so it's measure the shortest side. They're not told which side to measure, so they probably have to measure 2 of them and check which is shortest. And then measure the largest angle. Now they probably can see which one's the largest angle. We know that the largest angle is opposite the largest side, and that's something that becomes quite relevant when you do trigonometry. It's quite helpful to know the largest angle, and it's actually quite nice to try and explain why that is to students because they don't always see it. That idea of that kind of having to stretch to fit the sort of larger
dynamic
side.
Joe.
Yeah,
that's nice.
I mean, the thing is, my students never kind of know it without me explaining it, and it's like, look, if we have these 2 legs that are stretching to fit this really long side, that angle's going to be big, and they never sort of intuitively see that.
I like the contrast there between Boss Maths on GeoGebra, and that was your dynamic demonstration there. Is that available to download?
I do a fair amount of gestures when I'm teaching.
I like it. You want to patent that. It's good.
So yeah, they're measuring with a protractor there. So it's interesting to see that come up in SATs. That was from the sample assessment. I haven't checked to see whether it's actually come up in the last few years. This was in 2016. This kind of reminds me of an old Key Stage 3 SATs question.
But again, all GCSE, right? They would not be out of place at all.
You give this to probably my Year 8s at the moment, and half of them won't know the answer.
Yeah. That's a good
So they're having to use vertically opposite angles.
Yes.
Did I mention this last time about vertical opposite and what it means? So I told you this about how it means vertex.
Yeah, and I wasn't happy at that.
So we got A is 160 vertically opposite, and then they have to notice those 2 right angles, and they have to notice they have a quadrilateral there.
That's the big one, because that is, you kind of, I'd call that a triangular quadrilateral, right? It's suspiciously like a triangle. Do you know what I mean? It looks, you could glance at that and think, well, there's a lovely triangle.
Yeah, they're not going to think quadrilateral when they look at this question.
No, they're not.
And they're going to see that as, and so once they've realised it adds up to 360 degrees, then they know what to do.
Yeah.
But this is SATs. And the thing is, what we have to remember is, like GCSE, grade boundaries are low for SATs. So even though it was in that assessment in 2016, we can say probably half of the kids got it wrong.
Yes.
So we can't assume that because it's in there, they can all do it.
They've experienced it. Just the 1 mark again for being there. That's all you need for that.
This is a 2 mark question. We've got to show your method bit, so we know it's 2 marks there. Yes. They give them a bit of square paper.
Yeah.
A shaded isosceles triangle, isosceles in bold because they're telling the kids to look at that word, is drawn inside a rectangle, and we have to calculate A. So what we need to know here is it's a rectangle, therefore it's got a right angle in that bottom left corner. Yeah. And then we can work out the one at the top, and then we can work out the one inside the isosceles triangle, and then we can work out the one at the bottom of the isosceles. God, there's a little step. 2 marks. And what have we got to work out? We need to know it's a right angle, then work out the one at the top, then work out the one next to it. We know that that's 38 because I can see an alternate angle there, but they won't be thinking that necessarily. And then you've got that isosceles-ness of it.
That's tough. And this is just standard SATs. They're all doing it. Wow.
So that's it for secondary, and then we come in with. Sorry, that was it for primary. Then we come in with secondary, and we've got all this angle stuff. Angles is huge. It kind of cuts off at A level. Yes. And at A level we've got trigonometry, but there's no other angles.
But you get quite far down that list before they get to something new then,
yeah,
right?
so basically all the everything in the first, let's say three lines there.
Yes.
Notation, estimating, straight lines, triangles, quadrilateral, that's all done at primary.
Have they done a bit of tessellation? I always assume they've done that, but maybe they haven't.
The thing is, tessellation's not even on the secondary curriculum.
Yeah.
As far as I know, it's not specifically mentioned on the primary curriculum. And in terms of how it fits in secondary, they can ask a question on tessellation, but they'd have to define it in the question. So if AQA decide to have a tessellation question in there now, they are allowed to do it, but they'd have to say what tessellation means.
Right, okay.
Whereas it used to be that they could just assess tessellation and assume that it was a known term, whereas it's gone from GCSE
I mean, it's a nice way to get deeper into...
I wouldn't teach angles and polygons without doing a lovely tessellation lesson. It's one of my favourite things to teach, but it's certainly not on the curriculum anymore. Quadrilateral properties, which is horrible. Sorry, I shouldn't say things are horrible, but I know most maths teachers hate teaching properties of a rhombus, properties of a kite, all that sort of stuff. People don't like teaching that. I'm assuming they don't do in much detail in primary school, so they might know. I mean, I like to blow my year 7's minds by talking about how a square is a rectangle.
Right,
but
I'm glad you said that. I struggle with that, you know. Whenever it gets to, is a trapezium a rectangle or a rectangle a trapezium and all that, I'm like...
Well, the thing is, with rectangle, it's easy to remember because rectangle literally means right angles. So something with right angles is a rectangle. So a square is a rectangle. A trapezium doesn't have right angles, so you can't describe it as a rectangle. Rectangle means right angles.
But a trapezium could be a rectangle.
A rectangle is a type of trapezium. I mean, trapezium is well. Let's not do the whole thing on quadrilateral properties. I've got a presentation that I do at conferences on how our current definitions I'm not happy with. Having done research on how it used to be, we've lost some words like rhomboid. We should still have rhomboids.
I remember you saying something like this.
And there's a few other words that have gone that really made a lot more sense.
Yes.
So yeah.
That's strange for you to refer to some old textbook and look at the vocab. Yes. Okay. Fantastic. Right.
Parallel lines we've done a presentation on. We've done that
Topics
one.
in depth.
Polygons and tessellation, angles and polygons. In my book, out recently.
Plug everybody.
Compendium of Mathematical Methods. I have a
Surprised
chapter.
it's taking you that long to get that one.
I have a chapter on angles and polygons, and there are many methods. Yeah. And most teachers teach the whole n-2 times 180.
That's what I do.
There are numerous methods. I don't really like the n-2 times 181, to be honest. It's not my favourite. But yeah, so that's a really huge topic. Bearings, challenging, lovely.
That's one word for it.
Circle theorems and trigonometry. I would say it's not quite. It's not quite an angles. It's not quite sort of same thing, but it's still to do with angles. But we don't really need this other angle stuff to do trigonometry. Whereas for circle theorems, we do need the other angle stuff.
Yes. Okay.
There are links with similarity, with congruence, with constructions. It all links to angles. And I've put measure of turn at the bottom there because I did this presentation once and I got a bit of heckling because I was criticised by an audience member for daring to talk about angles without making my whole talk focus around measures of turn, which is what an angle is. And my point is that when we get them in secondary school, we shouldn't assume anything.
Yes.
But one thing that is normally something I find with my secondary students, not all, but the vast majority get what an angle is. Okay. So I don't teach from first principles this whole robot thing and the measure of turn.
As you say, even if they didn't get it in year 2 or whatever, they've had 4 years worth.
So there was that. If they don't understand a measure of turn, then we shouldn't be doing any of this. But we can't start from scratch all the time. No. And so I apologise for the first time I did this presentation. I didn't mention a measure of turn, and I appreciate that's what an angle is. But I'm saying that is assumed knowledge at secondary school. Okay. So what we're doing today with Angle Basics is just these things here.
Okay, that's interesting.
But I've already talked a bit about the kind of the measuring bit. Mainly we're going to do straight lines and triangles. Okay. So I haven't got time to do the whole lot. Okay. So we will just do those two things.
Maybe in the future we'll be back for that. Who knows?
Well, I could do a whole thing on vertically opposite angles. They're really interesting. Yeah. But these are such small little things. Okay. This was some of my year 7s a few years ago. These were the same year 7s that had the 2 lessons on angles, and I gave them. I think this was an assessment
Okay.
I didn't write the assessment, but the assessment said construct these angles using a protractor. And he's done 32 and 121 pretty well, but then he said the protractor's not big enough because he hadn't been shown specifically how to do a reflex angle, and he hasn't got the reasoning skills to figure it out for himself. That he needs to he needs to do 360 minus 236, and then he'll be able to do it.
I've got a point to make here, Jo.
Go on.
Right. See if you agree with this or not, right? So this is a point I've been banging on about. So I'm obsessed with the importance of retrieval. Mm-hmm. So mistake I used to make for many, many years. Teach the kids something, assess them straight away. They're amazing at that. Let's crack on with the next topic. And maths was always taught and assessed in these nice, tidy little boxes. And then I obviously learned far too late that unless we regularly expose kids to things that we've taught in the past, they're going to forget it. So, right. But here's the thing. Say you just decide to make up your own starters or your own low stakes quizzes. Mm. The topics that teachers tend to include are things like fraction operations, sharing in a ratio, solving it, the things that are easy to write and easy to assess. How many times when you're writing a starter would you say draw an angle of 121 degrees? Because you've got to think, right, I've got to get the bloody protractors out, I've got to do this. Yeah. But unless we cover everything in these retrieval opportunities, this is the stuff that happens, right?
You know what? I've been writing my retrieval starters this term, and since September, and I have not yet included anything that involves measuring.
Measuring, rotations tend to get left. All the stuff that's a pain, you leave it out.
Or even just the size. You know, I print them out, and it's quite small.
Exactly right. Yeah. So when they get a bit older, like all the straight line graph stuff, it's just the stuff that's a hassle. But then it's the stuff that kids forget.
You're right. Yeah.
There you go. That's my big contribution for today. Done.
I don't like it that he spelled protractor wrong because it says it at the top of the page. So
not the biggest issue, but good point. Good point.
So this is the problem that they're not. You're right. I mean, I didn't used to do retrieval starts at this point, whereas my current year sevens, because I do the whole last lesson, last term, all that, and then it has last year. So my current year sevens get year 6 stuff that we haven't done yet in year 7 fed into their retrieval. So I've had a few angles questions, and it's really interesting. They love it when they get an angles question because they always say, "Oh my god, we did this last year," because they haven't seen it with me yet. Nice. But after half term, they're getting a measurement one.
There you go.
And the thing is, they've all got a little math set. These keen year 7s,
of course,
so
of course. They need to practice with it.
No, this is my marking. I got a bit annoyed. This is when I used to be able to mark in any colour I wanted, so I marked in pink. Nice. And this was me marking someone who'd been given a homework on drawing angles, and every single question he did badly. So it was that first one. He basically he hadn't used a ruler, so it just gone all sort of wobbly at the end. And even though he'd measured it right, it was like, what are you doing? 142. He'd done 145. I don't see how you can be 3 degrees out unless you're really rushing it. The 74 degrees, he used the wrong scale on the protractor. That's obtuse. Yeah. And this one, he was meant to do 295. He correctly took it away from 360, but I don't know what he did because that's not 65 degrees. He labelled it 65. It's not 65. So I don't know what he was doing. But what I did notice was all over the place are some column method subtractions.
Yes.
And I'll come to this later. But let me use a calculator here because that is just slowing down then practicing angles. Yeah. This is a classic example of a calculator is a good idea in this
Yes.
I mean, look at all that. He's working all these things out. That's not what I want him doing. I want him drawing angles. And
you don't want him thinking hard about the arithmetic and not having enough attention and effort.
Because you take a student who's really weak at arithmetic, and that's going to have a massive impact on their success in this topic, and it will have a massive impact on their success in everything. Yeah. Unless you take the arithmetic out and say just use a calculator.
And you're a big fan of just using the calculator in as many topics as possible, so they get completely comfortable with it.
They're really good at calculators.
Yeah, good point. Good point.
This was a same test, different student. Look what he's done there. He was asked to work out angle A and B, and he's written 62 for angle B because he's assumed that's isosceles. There's nothing to say it's isosceles.
Yeah.
That was probably a case of seeing isosceles questions in class, the lesson before.
Yes, I'm sure it is.
And hasn't even had a go at A, even though that's just a quadrilateral. And they're stuck together. Maybe that's confusing, that it's a quadrilateral that's stuck to a triangle. But these are some sort of classic mistakes.
That's good, though.
This is probably the most annoying thing I've ever marked because I had to give him full marks for it.
Okay. Because
it was testing whether they could measure with a protractor.
Okay.
They measured angle A, he got 141. He then moved his protractor over and measured angle B and got 40. I had to give marks for within 2 degrees.
Oh, yes.
Obviously, he should not have been measuring angle B. He should have been subtracting from 180 because that would be the logical thing to do.
It tells you in the question, though, right? Measure both.
Yes, and the thing is that this question is not a good question, but also it's frustrating that when I mark that, I'm thinking he has not at any point connected this with everything else he'd done in angles. He's not thought, oh, hold on, they should add up to 180.
That's interesting.
What's he doing? Like, this is how can he not realise they're angles in a straight line?
You've done well not to like write any bad words.
I
or
probably
anything
did
like
underneath.
Yeah.
But the thing is, it's interesting because I could have given him 2 separate angles, and then this wouldn't have bothered me. But the fact that they were given as on a straight line and he's not noticed, that's really frustrating.
Yeah, bad question that.
Yeah. Right, so let's say we're at the teaching bit now. So this
that was the build-up.
That was the build-up. So this is the teaching. So let's say they come in year 7 and we want to start teaching angles. We've got a couple of weeks to do it. And then we like to start with some narrative. We like to a bit
of storytelling.
Once
upon a time.
I do love a storytelling bit of the first lesson. Okay. And actually the question, they'll know there's 360 degrees in a full term. But do they know why there's 360 degrees in a full turn? Like, where's this number come from?
Okay.
So I might start with a bit of why 360.
Okay.
Do you know do you know why 360?
I mean, I wouldn't want to spoil the surprise for everybody who's watching it. I'll tell you what my instinct would be. That 360's been chosen for no other reason that it's just got tons of factors. So
you're absolutely right. It is because 360 has a lot of factors, and this comes back to the ancient Babylonians. And in ancient Babylon, they said there were 360 days in a year, but that's not because they didn't know that there were 365.25. Nice. They knew that, but they, for convenience, said there were 360. And if you imagine that they're making kind of circular graphs to show the days of the year, and they wanted to split those days so they'd have the 360 kind of intervals in a year. So it was all, they chose 360 because they worked in base 60. That was their number system. And because 360 has a lot of factors. So, even though a lot of people say, well, they thought it took 360 days for the Earth to go around the sun. That's not true. Ancient Babylonians are very clever.
What do they do with the missing days?
They had a way of adjusting for it. I mean, we adjust now for the 0.25 by having leap years.
Yeah, okay.
So they had their own, I don't know what it was, because I don't know much about ancient Babylon, but they had ways of adjusting for it. So they did know how many days in the year. They were very clever, very advanced.
Yes.
They chose 360 because it was a convenient number with lots of factors. And the thing is, if you're gonna tell your students that, you can't just talk about ancient Babylon and then just as if they know what that is.
Well, yeah.
So I found some ancient Babylon stuff to show them. So I have a picture of ancient Babylon, not an actual photograph. I have a diagram of where Babylonian Empire was.
Wow.
See, I didn't know this. This is me learning. And then I have a timeline. And you can see that the sort of second line down is ancient Egypt, that big and it's a really long empire that was a very long period of time. And if you go sort of 3 down from that, is a pink one, Babylonian Empire.
There it is.
So just to put that into context, they can sort of imagine the kind of time we're talking about, and how this idea of 360 degrees has been around for a very, very long time.
And it makes a difference to kids, this, doesn't it? It's just a nice way in. It's
a couple of minutes.
Exactly. No, that's nice. I like that.
I've recently taught the metric system, and when I teach the metric system, I always talk about the French Revolution and where metric units came from.
Okay.
And Don Stewart, in his slides about angles, he talks about how there was a plan to use 400 degrees in a circle. So when they went metric, when they said that we want 100 centimetres in the metre and all that sort of thing, they said, let's say there's 400 degrees in a circle, but that wouldn't be 400 degrees, so it'd be 400 grads. 400 grads.
Right.
And actually on our calculators, we do still have a grads, there's radians, degrees and grads, so we do still have that button on our calculator.
Is that what it means? Is that what it...
Yeah, that's what it is. It's 400. Actually, am I right about that? Because now I'm thinking there's 100 something in a circle. I don't know much about this.
But the grads thing is, it's like degrees, radians, it's an alternate.
Yeah, it's another way of measuring an angle.
Good fact, Joe.
Yeah, so there's this interesting stuff.
Yeah.
And we say, look, we went for 360. It's a convenient number to use, and then we've used 360 for thousands of years. And 360 has a lot of factors, which is really helpful. We can talk about, at this point in secondary school, we can start formalising some things. So we can say that they're used to seeing angles just marked with maybe a lowercase a or lowercase b, and we can start talking about slightly more formal ways of using angle notation. So for example, that we would label a triangle should be labelled, say, ABC. So we call triangles after 3 capital letters. Because I've had students before, I'm trying to think what topic it would be, but say they're told to sort of draw something and they have to, it's something to do with coordinates on a coordinate grid. And quite often they don't know that, say, a quadrilateral, A, B, C, D, the corners need to go in that order. I've seen students kind of get into a mess with that before. This is sort of stuff that we should be saying in year 7 and not just kind of saying, oh, triangle ABC, without explaining what we mean by triangle ABC.
So a couple of things on this. One, I don't do that enough, I'll tell you that much for free. I'm not consistent enough to label the side as the lowercase version of the angle.
Yeah.
That's number one. And secondly, that's the kind of thing that needs assessing or developing in separate from anything else. So if you start combining that with measuring them at the same time, you're asking for trouble.
Yes, although so Boss Maths is a good example of this. They have a couple of lessons just on notations.
Wow.
So and I've not seen that anywhere else, and that's one of the things I love about Boss Maths is that sort of thinking about like you say, separating it, because they haven't seen it before, and they need to be able to. You can't just start throwing in notations. They need explicit teaching of the notations. Right. And then the stuff about equal sides and the hatch, a lot of teachers don't know they're called hatch marks. So the hatch marks showing equality of length.
Is that what they're called?
Hatch marks.
Hatch marks.
Yeah. So I explain this to my students fairly often at the moment. Because I've been doing these retrieval questions and I've been putting, say, isosceles triangles in.
Yes.
And then some of them say, oh, what are those little lines? And it's like, well, I'm sure you've seen these in primary school. These are hatch marks. And they're telling you that something's equal length. And then I explain why sometimes we have 1 and sometimes we have 2. Because if you have 2 on one line and 2 on another line, then those 2 lines are equal length.
Let me ask you that. So there's nothing wrong with, so that one on the bottom left there.
Yeah.
2 hatch marks is fine. That you don't always have to. If you
don't
always have to have
with
one.
No. You can as long as you have a matching number, then you're saying these 2 lines match. So I could put 10 on that line and 10 on the other line.
Wow.
I'm saying that they match.
Okay. Nice. I like that. Yeah.
And then the same idea with the parallel little arrows. I have a single arrow. It means that anything with a single arrow is parallel to each other. Anything with a double arrow is parallel to that thing.
Do you have a name for those?
No, I call them parallel line arrows. I don't know what the name is actually.
Let's give them Plaro.
I'm not sure it's going to catch on. Robert Record in the 16th century tried to invent terms like that and it didn't catch on.
But we have the mass marketing parates behind us here, so if we say it Plaro.
I don't want to call them Plaros.
Okay.
We don't use that little notation there. Look, AB is parallel to DC, or AB and then the double line, which is commonly used throughout the world. And I'm not saying we don't use it in this country, but I never write like that. I mean, they do a lot in America.
They're off kind of slanted.
Yeah, I normally see them as vertical.
Yeah.
But that idea of using a couple of parallel lines instead of writing is parallel to. We don't really use some of that notation in secondary school perhaps as much as we should and as much as they do in other countries.
I mean, put a couple of Plaros on there, that might just stick in it, won't it?
I'm not calling them Plaros.
Well, we'll see.
I talked about
you love these hats.
I talked about it with you last time. In that, if we are going to introduce this notation, we have to be clear what we mean by it.
Yes.
Because I've had students before who have not answered questions correctly because they have not understood that angle ABC means you start at A, you go to B, and you end at C, and that's the angle we're talking about. If they're not told, we shouldn't assume that they know what this is.
Yes.
And that's why the top one, just a B, I'm not comfortable with that. Yeah.
And can I just ask on that as well? And I don't think we talked about this last time, but do we always assume it's the non-reflex? Or how do you indicate? How would you indicate that B was a reflex?
I was in a big discussion on Twitter about this once.
You know what I mean, don't you?
Yes. In fact, after I did this particular presentation to a group of primary teachers, someone asked me that exact question at the end. I didn't know because so if I say ABC and it's there's say an obtuse angle, I want the obtuse angle and it's very, as someone said, in an exam they'd never expect you to give the reflex, but that's not good enough, is it?
Yeah, of course.
Now I think it's to do with, if you look at how they do it in GeoGebra, and then some other people refer to other conventions here, it's to do with clockwise or anti-clockwise.
I think that's right, and I think it's you assume anti.
Yeah. It's a good. It's the thing is that's the sort of thing where if we don't know, I mean, it's not good enough, is it? Because this is math. I know a lot of people say mathematics isn't about this sort of accuracy, but
of course it is.
Accuracy of communication is so important.
Well, the whole point is it's supposed to be unambiguous, isn't it?
Yes, exactly. That's what we're all about.
One of its big plus points.
Yes, we're all about not being ambiguous.
What are you calling the little hat? Is it a little hat?
I'm calling it a hat, yes.
that technical, yeah? Right.
And then obviously if we're going to start using thetas, which I think is quite a good idea.
Theta's a good one.
We don't want them to see thetas when they first meet trigonometry because that's too much at once.
Yeah.
So say, hey, you know what, you may have seen a little a for your angles before, but I'm just going to use a theta and it's a Greek letter. And then we talk a little bit about Greek letters. And then I've done that recently with my year 7s and year 8s, I've mentioned theta to them, and I've just said I'm just going to use it as a symbol. And
it makes it look a bit different from perhaps primary school. It's good. I like it.
Now you've just said not to do this. So when we talked about, you said do a separate lesson on the notation. Yeah.
Your separate activities. Yeah.
Yes.
Exactly.
So you're saying that we shouldn't try and introduce, we shouldn't try and get them practicing angle stuff and learning new notation at the same time.
That is what I'm saying.
However, once they've learned their angle, stuff,
then
they
bring
can,
them.
Then
I
here,
agree.
so here they're practicing. So here, if I want them to give the measure of angle RQS, they go from R to Q to S, and the answer is 25 degrees.
Yes.
Yeah. So this is a activity where you can give this to your secondary students who you think already know how to use a protractor.
That's really nice,
but you're saying actually we're not practicing the protractor
Yeah,
use, we're practicing the angle notation, but really you're checking their protractor
You
use.
want the vast majority of their attention to be on reading the protractor,
Yes.
not consumed with worrying about too much about notation.
Yes,
Yeah,
absolutely.
That's right.
And then actually if you look at, say, the bottom one, angle UQV,
UQV, yeah.
that's an interesting one because it doesn't start at 0.
Yeah,
So, you
it's
know,
an
that's
interesting
from
one.
90, and then we'd have to sort of,
Yes.
and again, if it didn't have a scale on it, it'd be easier because I'm just counting.
Well,
See, I like the idea
possibly,
of counting.
possibly.
But yeah, so that's just a
I like
sort of, I mean, that's an activity where
Where's that from?
that's from Maths with Pizzazz. Do you know that set of resources?
No, I didn't know.
That is an American set of resources. They've got lots of code breaker activities. There's absolutely tons of them. The problem is they're a little bit old, so the PDFs aren't great. But basically, if you're the sort of teacher that likes code breakers or things, I mean, this one, see all those letters down the side?
Yes.
There's some kind of, once they've worked it out, they work out a word or something.
Wow.
Basically,
I see.
there are
Yeah,
pages,
yeah.
and there are, I mean like hundreds and hundreds of code breaker type activities in Maths with
How are you
Pizzazz.
spelling pizzazz?
Pizzazz, apparently.
Of course, yeah, of course. Fine, perfect.
They're on my blog because
Yeah.
I put them in a Gems post years ago, and I'm probably not meant to have them because they're the kind of thing that are like an old set of resources that someone's PDF'd and actually someone had to buy them at one point.
Yeah.
But yeah, there's a few nice bits and pieces in there.
I like it.
I would bring in the word supplementary in year 7.
Yeah, this is interesting.
And the idea
And
that,
they've never met this.
no, they won't have seen that vocabulary. And the idea, I mean, complementary as well. Complementary is two angles that add up to 90 degrees.
We had this big discussion last time,
Yeah,
didn't we?
and the thing is, I don't think we need the word complementary. There's nothing wrong with talking about it, but we don't really need it. But I would say I use supplementary quite a lot. Whenever I say add up to 180, I say they're supplementary. So I try and use that word a lot. And it comes from the Latin to supply what is needed. So this angle is supplementary to that angle because it supplies what is needed to meet 180.
That's good.
Yeah, so, and also some people say that you can remember this because it begins with an S, just like straight line. So supplementary straight line, they begin with an S. The thing is, it's interesting, they don't need to be next to each other. So look at those two angles at the bottom, the 60 and the 120, they are supplementary angles.
Oh,
Two
really?
two angles that add to 180, that's all we need. They don't have to be adjacent.
See, this is what fascinated me last time when we talked about the parallel lines, because I only ever use alternate, supplementary, corresponding with specific regard to parallel lines,
Yeah.
but it isn't.
Oh,
it's
no.
more general than that.
Yeah, but I don't know, I think I might have mentioned last time, for years I said the angles in a triangle are supplementary, and I shouldn't have said that because supplementary is two angles.
Oh.
And so I was getting that wrong. I was saying they add up to 180, thinking that's what supplementary meant. Actually, there's three angles in a triangle, so you shouldn't use supplementary.
Okay,
there.
good fact.
Now we could do a whole load of work on this, the definitions.
Yes.
Acute, right, obtuse, straight, reflex, revolution. So we could do that.
See, there's your dodgy one, right? Look at that obtuse between 90 and 180.
Yes,
So
it's not very clear. So this is a good opportunity to review inequality symbols because you're right. Rather than use that language,
good reveal there, Joe.
rather than use that language, we really could be using inequality symbols.
Nice.
And it's a really nice opportunity because actually you're right. The acute is less than 90, and that's a strict inequality. It doesn't include that 90.
Yeah.
I don't think we need to spend a huge amount of time on this because they've done this a lot at primary school. But there are ways to remember. I mean, they're alphabetical order for a start. You know, acute, obtuse, reflex. They're in size order, so that's pretty easy to remember.
Good.
That reflex is bigger than obtuse because R comes after O in the alphabet.
That's really good.
There's some nice etymology here. So, like, can you think of anywhere else where you hear the word acute?
I mean, I put a little fact for you here. When I was dating, right, and I met my wife, my online profile was I'm looking for a cute girl.
That's terrible.
So that was
And
it.
she actually
spelt like a cute
and that's
font.
how you met her.
Yeah, I didn't get many replies.
She's not a
but she was
mathematician, is she?
no.
Amazing.
Took
So
pity on
she
it, I
wasn't
think.
put off by that.
So that's where I met.
Okay,
That's where
so-
you might see it in real life.
That's not the sort of example I meant. There is an example that's nothing to do with maths of where we use the word acute. When you go to the doctor. You might say.
Oh yes,
I'm in
acute pain. Yeah.
And think about sharp.
A sharp pain.
Yeah. So it's to do with the word sharp. Yeah.
Oh, that's interesting.
So acute is from the late Middle English describing a disease or its symptoms. So you would say sharp, and it comes from the word I can't pronounce Latin, acus or acuus or whatever, and that means needle. So the sharp end, sharp end of a needle, sharp pain, sharp angle. It's all to do with sharp.
Very interesting.
Obtuse.
You love a bit of etymology,
I do.
don't you? Me too. Again, it's good because it helps them kids draw connections. It taps into story structure, which we know is powerful. There's a lot going for a bit of etymology.
Obtuse, I don't have it on the slide, but I looked it up on my way here. I checked obtuse. I thought, why haven't I put it here? It's a bit of a funny one. Obtuse came from the Latin to beat against. So we're beating something, and when we beat.
Punch.
Yeah, and when we beat it, we make it dull or not sharp.
Is that right?
Apparently so. So it comes from the idea of beating something until it's not sharp, it's blunt.
It's interesting because you mentioned blunt before, didn't you, at the start?
Yeah.
I've never thought of an angle as blunt.
Yeah,
Do you still prick yourself on a...
You're right.
Prick your finger on an acute angle. An obtuse angle.
You're right. You can. Yeah.
That's interesting.
Have you ever had a child call it an obese angle? Because that's quite funny.
That's good.
Yeah.
I think it works, doesn't it?
Kind of. Although I don't think, because if it means not sharp, it's a bit maybe. I'm guessing they have some kind of shared origin, those two words. But reflex is interesting.
Go on. I have never thought of this, so go on.
So reflex comes from the Latin for bend back. And we have two words. So first we've got flexing. I don't know if you sort of flex something, flex a muscle, kind of bending it. But also reflect. So reflect, is like where it bounces back. If something reflects.
Okay.
It's related to reflect. So basically the idea is a reflex angle is to do with bending back, and you get that idea of kind of a reflex angle. If you imagine kind of someone bending back, they're flexing. But it's related to the word reflect, which is something to do with bouncing back or bending back. That's good. Light bends back if it reflects.
I've only just discovered, so I always used that etymology online, but it's really good, like that diagram you've got on right. That's just if you Google etymology and then the word, you get the lovely flow thing like that. It's beautiful, isn't it? Yeah, nice.
Very good.
Nice.
Now, I used to have my students do this, and it was this one, they'd already done angles and parallel lines, but you can change it for the basic angle facts. And I used to get them to write down their definition and draw a diagram, and it was so revealing because they do all sorts of crazy things with it. So this was something I used to do when I worked at a grammar school, and it would be either at the beginning I want to find out what they know before I teach them angles, or it would be kind of at the end of teaching angles. And so they might not know supplementary at the beginning, but after I've taught them, they should know what supplementary means, and you can see their little diagrams. The diagrams are really telling. But actually, I've kind of moved on from this now, and I think possibly Freya models are more effective. So I've got some, Freya models. For people that don't know, that's where there's various formats, but you can have a definition. You might have some facts or some characteristics, and then the important bit, the examples and the
non-examples are the key. And a little Freya tip for you here, right? I'm sure you know this, right? But I always say to the kids with the non-examples, make as interesting a non-example as you can, and one that somebody may think is an example. So they get them close to the boundary. Because otherwise, your non-example could be you draw a duck there or something like that. Do you know what I mean?
Yes, I see what you mean.
So if you make it interesting or as close to...
I mean, the thing is that for anything in geometry, these work really well. They're a bit harder to do for things outside geometry, but here's an example for complementary angles, which are two angles that add to 90.
Yes.
And then there's an example for triangles, and so these basically... There's a blank one there. They work really well. I mean, this one is for a primary school Freya model, meaning from a dictionary, and then draw a picture of it, write an example of what it is, and write an example of what it's not. So these are really nice activities. But there's a lot of vocab stuff in geometry. We use really complex technical words all the time when we teach geometry.
Just whilst we're on Freyas, so as you say, they're great to use before you teach something to figure out what the kids know. They're great to use immediately after, to as a bit of an assessment, but they're also a great retrieval opportunity. So you imagine 3 weeks later, if you've moved on to another topic, you hand out a blank Freya on angles, so it's testing what they know, but also just not in a fact retrieval way and getting them thinking a bit deeper. So
I had a great idea for Freyas, and I didn't do it this year. I had this big Freya, so I was going to do them as homeworks. So I was going to start the year by introducing the idea of Freya models and do some in the lesson, and then I was going to say that whenever I introduced a bit of new vocabulary, their homework that week would be to fill in a Freya model, but I'd want them to. So I would hope they'd all look a bit different, and then they were going to bring that back in. I'd show the best ones under the visualizer, and then they'd all get their Freya models handed back to them, and they'd put them together like treasury tagged into a little booklet.
Yeah,
so
yeah.
by the end of the year, all the children would have a booklet of frame models.
Good revision
Yeah,
cards.
I haven't had time. The thing is, I have so many ideas, and then I take on a new class. I actually can't do all these things, so I haven't done it. Maybe next year.
Maybe.
So let's have a quick look at just in detail
wow.
two things.
Dynamic.
So let's start by looking at straight line. So there's lots of dynamic software we can do to show that when we move this line around, the angles are already. I don't really like this one because of the decimals.
Yeah, but it's interesting. This is an interesting thing though. So I build a fair bit of dynamic stuff on GeoGebra, and this is true, I think, of all dynamic geometry packages. You've got to be really careful with the rounding, right?
Yeah.
So if you put it as round to like 0 decimal places or nearest integer,
Sometimes
you'll always get those funny
and
you've got to be really careful, haven't you?
The unexpected misconception, and the thing is that I haven't put it in this slide, but I have now got a picture of a child's work that I have marked where they've made this mistake. And the misconception, as you know, is where they think that angle over there is 150 because they see two angles in a straight line, and their teacher always told them that two angles in a straight line add up to 180. Right. And you know, it's a sort of mistake that until you see it, you find it hard to believe.
Curse of knowledge again, right?
Yeah, and I think because I taught in a grammar school for the first 5 years and I never saw this, and then I moved to comprehensive and I'll never forget the first time I saw it, and I was observing another teacher teach, and I was walking around looking over the shoulder of students, and I was like, what have you done there? And now I've seen it a fair few times, and I think it's one of those things where people who haven't seen it think, no way. But actually, yes, it happens fairly often.
Joe Morgan, let me ask you a question. Right. So let's say, for example, you are teaching angles on a straight line.
Yeah.
And you don't see that. Your kids are all doing it fine. Are you exposing them to that, or are you only mentioning it if it comes up?
I am exposing them to it. I know that's controversial.
No, I'm just genuinely interested.
Yeah, I think increasingly now I show them misconceptions up front. And I say, can you believe that some people would do it? And they're all like, no way! But it's actually a really memorable bit in the lesson for them. When I show them something, I mean, it happens fairly often where I say, you know, I'll like say the other day I was teaching indices, fractional indices, and I was saying 49 to the power of a half, and I just taught them that means the square root. Yeah. And then I said, here's a really common mistake, and I showed them a kind of spot the mistake question where they'd done like 49 times a half or whatever. And they said, no way would anyone ever do that. Well, I was like, well, you guys have just learned this.
Exactly,
I bet some of you do this when you forget.
Absolutely.
But I think they remember those things, and I think it's worth pointing it out.
You're right. I mean, my limited reading of the research suggests that they've got to have some kind of knowledge beforehand of the right way to appreciate the wrong way. Otherwise, you can imagine kids getting it muddled up.
Yeah.
So I agree with you. Give them kind of some success, get them feeling pretty good about it, and then this becomes a really powerful learning opportunity.
Absolutely. And the interesting thing here is, some people think it's to do with the wording, and I think there's lots of things. It's to do with the wording, it's to do with the way you teach it. But there's 4 different options here. So I always used to say angles on a straight line. And they are angles on a straight line. So we could say angles that form a straight line, that's one option. We could say adjacent angles on a straight line, that's the one I do.
Okay.
Angles at a point on one side of a straight line, I know. Avoid that. Actually, I've got one more. Sorry, I just added this the other day because someone tweeted it and he says angles in a half turn, which is not a mouthful. So maybe preferable to the other ones which are a bit of a mouthful.
So I've got something to say, Joe Morgan.
Go on.
Right. So again, we've had this discussion before. The problem with all kinds of definitions is, well, as we can see here, as soon as you try to cover all these kind of edge cases, the definition starts to become a paragraph, and it becomes so complex. So again, I'm all for this because especially kids have to write down their reasons in exams and so on. But again, the only way to get kids to really understand what this means is this combination of examples and non-examples, so they can compare what works and doesn't work. The mistake I've made for many years is I start with this definition, and the kids don't have a bloody, they don't have a bloody clue what's going on.
I mean, I'll show you some non-examples and some examples for this because I think you're absolutely right. I think the definition is not helpful. However, I try and say the word adjacent all the time. They need to know what adjacent means.
Oh yeah, of course.
And I've got definition of adjacent here. You know, I sort of talked about what adjacent means.
Nice.
But if I'm going to start saying every time I see that situation, I say they are adjacent angles on a parallel line, on a straight line. They do need to know what adjacent means. Yes. In America, they call them linear pairs, and we don't call them that at all. So linear pairs are supplementary and are adjacent. So that means. So rather than these are saying the pairs of angles below are not linear pairs. That's because they're not on a straight line next to each other. But the ones in the top row are linear pairs, and that means we know they add up to 180, and we know they're next to each other on a straight line. it's a silly term because sometimes we have 3 angles on a straight line. They're not always a pair. But it is less of a mouthful, and it is, and so, but that's what they say in America. So they would actually, their reason, if they were given A and they had to work out B, they would say B.
Pairs.
They would say
weird that.
They would say because they're a linear pair. Now, linear something might be a better way.
Linear's good.
It'd be nice to
start.
have a little
Linear's
phrase,
good.
a little catchy phrase like they're linear angles or something, like linear something.
Yeah.
And when we say that, we mean they're next to each other on a straight line.
I'll get working on it. So I've already done Plaro for today.
So now we use linear something,
I'll
which
be
means
onto that.
angles on a straight line that are adjacent.
Euclid.
Euclid.
He normally pops up in these presentations.
So the thing is that Euclid said, now just think about this, if a straight line set up on a straight line, so we have a straight line coming off it, make angles, it will either make 2 right angles or angles equal to 2 right angles. Do you follow that?
No.
So he's a bit confusing, Euclid. I don't
think he spoke English, did he? No. Is that a photo of him as well? Yeah.
That's a photo of him with his, what is that? What are those things called? Calipers or something? I might make that up.
Possibly.
Don't quote me on
So
that.
go on, what was it? Translate that for me.
If we have a straight line.
We need your dynamic geometry arms.
Let me find a picture of a straight line so I can explain it. If we have a straight line, like this one here,
yes,
and we have that orange line coming off it, so you could say, if we have a straight line and another line coming off it,
yes,
then you will, and then you have 2 angles, you will either have 2 right angles.
And within there,
you'll either have,
this bit I don't get.
You'll either have 2 right angles, because it's horizontal and vertical, they're perpendicular to each other, or you will have 2 angles that sum to 2 right angles, in other words, sum to 180. They used to talk about everything in terms of right angles. Right. So anyway, Euclid, this is classic maths. This is like absolute. This is a proposition in Euclid.
He looks a bit fed up though, doesn't he?
It's not got the most.
He's probably realised he's not phrased that quite as clearly as he could. He's committed.
They always talked about things in terms of right angles. So like a whole turn is 4 right angles.
So he wouldn't have been talking 90 degrees, would he?
He would have said right angles. He wouldn't have talked
in degrees.
That's interesting. I don't know whether Euclid talked in degrees. Well, I don't know. Interesting. I haven't read a huge amount of Euclid myself. Here's my examples and non-examples. So we have the 3 on the left are examples. They're adjacent. They're on the same side of the straight line. Therefore, they are supplementary. C and D are adjacent, they're same side of the straight line, therefore they're supplementary.
Yes.
E and F are adjacent, they are the same side of the straight line, but I've put that other line in just to show you.
That's good.
And then, this is not a comprehensive set of examples, no, it's just a few examples, no examples. So I have G and H are not supplementary because they're not on a straight line, but they are adjacent. They're just not on a straight line.
Yes.
I and J are on a straight line but not adjacent, therefore not supplementary.
Yes.
And K and L are not on the same side of the straight line. And maybe that same side thing's quite relevant there because they are on a straight line and they are adjacent.
They're good. They're good, those. And how are you using those? Are you stating that to the kids?
I don't really know how other people do it. That's how I do it. I literally say the words. I keep saying the same words.
People have a bit of choral response there, don't they? You're not a massive fan.
I'm not very good at that. This is white rows. Write a set of angles that add to 180. So in the first one it's A and B, in the second one it's C, D and E, but then when we get to the next one it's F and G add to 180, H and K.
That's nice. That's good, isn't it?
Yeah, and then you get down to say W, X, Y and Z, and you can see that X and Y do, but not say W and X.
Yes, that's nice.
Yeah, so that's a nice resource. And then this is also white rows. This is quite old from white rows. They've probably improved these since because these were from their very original materials. Is each statement true or false?
Yeah, that's nice. Yeah, I like that.
And that's pulling out those misconceptions.
Again, it goes. I mean, I know this is the whole point of what we're doing here, but it's so easy just to gloss over like angles on a straight line, isn't it? You can box it off in 5 minutes.
Oh yeah, I mean, I'm talking about doing an entire lesson or possibly 2 just on that fact, whereas previously I would have done, like you say, 5 minutes in the Year 7 lesson.
Exactly.
Are these straights as converse? So we're not telling you they're straight. We're asking you.
And we know kids struggle with this.
Yes.
Yeah. Those reasons. Nice.
So that's all white rows, and then it's worth. So these ones here, I might just say we'll work out. I mean, it's a bit boring to say just work out the missing angle.
Yeah.
But I've got the whole point in this is I've got them in different orientations. I've then got different ways of presenting it, and then now I've got 3. Now I'm not suggesting this is one activity, but I'm just saying that presenting the questions in various different ways, when actually rather than just ask a whole load of the top one, which is just a waste of time. So there's various ways we can ask that question.
The orientation's key, isn't it?
Yeah, absolutely. if you look at that last one, look, you can work out C using vertically opposite, but
Yes,
you don't
you can.
have to, because you can use straight line then a straight line. So you can work out B first, and then you see another straight line. And when there's, they find that quite hard when there's two straight lines.
Yes. Yes.
Yeah.
Good. I like that.
So this is.
Wow. What's it?
That's
Is that
good.
10 ticks? No.
It's Kazoom.
Oh, Kazoom.
Kazoom, and also CIMT has loads of this. You're right, probably everywhere like 10 ticks has lots of
Yes.
these. But what I like about this is the first few are just standard.
Yes.
But then it gets a bit more interesting. I mean, what's going on with those two at the bottom? They're just using angles and straight lines, like both
That's
those.
good, that.
But they're pretty challenging. So, you don't have to really give students a huge amount of those standard ones because they're just doing the same thing every time.
Yes.
But you can give them these ones at the bottom are still testing
Yes.
linear pairs.
You advocating calculator for this?
I am indeed. In fact, there you go. You read my mind.
That is very good. It's the animation that blew my mind there. That was
yes,
PowerPoint
absolutely.
in depth.
Why do this with? I mean, if you do column subtraction or any sort of arithmetic for this, you're slowing it down, and it's just not what you want them to do. And if you get a really students that struggle with arithmetic, you don't want to put them off everything. Let them use a calculator. It doesn't affect anything. You can get to practice arithmetic anytime.
Interesting.
This has got a little bit more reasoning in it. I mean, this is CIMT. There's nothing particularly challenging about this question, but if you want to know whether they understand angles and straight lines, here's a nice hinge question.
That's a good question, yeah.
They can get their, if they want to work out angle Y, they can't just jump straight to it. They're going to need to use, they're going to need to sort of spot a linear, I'm going to call them linear pairs. I've decided I quite like that. You spot a linear pair, and you could go with either of the two next to the 1, 2, 5,
Yes.
and then go from there. But basically, that requires a couple of steps, a bit more thinking, and it's just not your kind of boring, straightforward, it's not obvious. So that might be something to sort of check their understanding.
Yeah, good that.
So that was straight lines, and now we can look at triangles. So I said there's two big things we look at today.
Yep.
How do you have a big introduction to angles and triangles that involves some kind of tearing up a paper?
I used to. I mean, it's the classic, isn't it?
It's
And
the
when it
classic.
works, it's really powerful.
Yeah.
But yeah, I've had some lengthy experiences, let's say. with
So I
that.
mean, I think
You've been there, have you?
I did it. I think, yeah, and it's almost like I don't know where those ideas come from, because I don't remember anyone in my PGCE telling me I had to do it. But yeah, I found myself in my NQT ripping corners of triangles.
And
so
just remind us, they know this from primary.
They've done triangles before, definitely. They've done angles and triangles. Yeah.
Okay.
So that's kind of the classic,
rip,
where
yeah.
you rip the corners off and then you line them up, and sometimes
It is nice.
sometimes it's not kind of obvious how to line them up. And,
Yeah.
and I used to get to stick it in their book with sellotape, and then they sort of do a little. I think I even had them say proof. Oh, it's not a proof.
Ooh, okay,
It's a demonstration, definitely not a proof. But yeah, I did that for a while.
That's good,
I'm not convinced now, but.
And what because of the time factor,
It's
or
fiddly. I don't think they really need it. They already know this fact. I'm not convinced. I don't know.
I'm sometimes not convinced they see what it actually means, if that makes sense.
Yeah.
And also, here's one for you. Like, how do you know those are actually straight lines? That they make
Yes. Yeah. So that's one of the big things. So I have a load of options now. I think
Okay.
I've got 5 alternatives to this.
Wow.
And none of them are great.
Okay.
So
Lower your
the
expectations.
one thing to mention is you can do this for quadrilaterals as well.
Yes,
And I never did that.
I never did that.
I always did
I never did
triangles,
that.
but you can show that quadrilateral angles add up to 360 using the same technique.
That's good.
You could fold down the top of a triangle. Ever done that?
No.
You just take a triangle, you fold down the top. That's angle 2.
Oh,
You
yes.
can fold in the corners,
Yeah.
and
Oh,
they
wow,
meet
no,
on a
I-
straight line.
Oh, in fact, no, I haven't done this.
So you can see just by folding in the corners of any triangle that the 3 angles meet and they form a straight line.
Good that.
So that is it's basically without ripping them off.
That's
You're doing
not bad.
exactly the same thing. You're just folding them rather than ripping them,
It's nice, that.
and that's how it ends up looking. So you fold in the corners, you draw them, and you fold them out, and there they are.
It's a bit less fiddly than the.
Bit less fiddly.
cutter.
Same idea.
Okay.
Someone showed me that if you had 3 congruent triangles, you can just turn them around and you can see that the 3 angles fit together. Someone's done it there by getting the congruent triangles, and they've drawn stars in each corner and circles and little patterns, and they've basically shown that the 3 will always fit together on a straight line.
Yeah. Okay. Yeah.
Yeah, none of it's overly convincing, is it? You could use dynamic software, but again, the students have to believe, this kind of leap of faith
tricky,
there,
isn't it?
there?
That's nice though. It looks nice.
Yeah, it looks nice, and also this has got those nice rounded angles, although, like you say, maybe they don't always add up to 180. But the idea is that as I move that round, I can see like the red angle's getting bigger, it's getting bigger at the top. They are the same angles, and they always add to 180.
It's not, but again, there's something not right, something not quite intuitive enough, or there's something, isn't there, with all of these? This is interesting.
So this is measuring. And it's just, I've got this on TES as a standard resource. You measure the angles, you write down, and then you say, what do you notice? Now they know what the answer is. They did it in primary school. But what do you notice? And they should notice if their measuring is 100% accurate and perfect.
That's a biggie, isn't it?
They should notice they add up to 180. They already know this. This may be good if you want them to do some measuring, but I'm not a fan.
Yeah, okay.
This one
free magnifying glass with this one.
This one. Now I know Danny Quinn's a fan of this, and I like anything that Danny Quinn likes, but this one I really struggle with. This is to do with moving around. If you imagine you're kind of standing in the corner of a triangle and you're pointing up towards the top, and you kind of move up. Do you know what I mean? So you start facing that way and you go up like that. I mean.
Keep going with that pen. Here we go.
So you do the first angle, you come up to the top corner. Do the second angle, you come down to the next corner, you do the third angle, and you end up basically facing the opposite direction, which means you've turned 180 with your pen.
Yeah.
I think it's massively confusing. I'm not a big. This is NECTM. I mean, I get the idea, and people are saying this is way better. This is dynamic angles.
Yes.
Oh, confusing.
And just for my own sanity, like you can't read that. Like, it's not my eyes. I've suddenly gone mid-presentation here. That's small, isn't it? Yeah.
I can see it says move the arrow to the next vertex. I've got my contacts in, I've got pretty good vision with my contacts in. It's available to download. The links in the notes.
I can't wait.
Anyway, this is from Ed Southall's book, Yes But Why, which was really one.
And this is what you like? Is this the are you building? You don't like those ways?
No, I don't like any of them.
Okay.
Ed Southall's book says it may be tempting to help students to discover this fact by measuring. Be mindful, they're going to measure with a small margin of error, and they end up thinking, oh, it's approximately 180. And he's saying, basically, be very careful of this. So he's saying it's a nice demonstration, it's not a proof. He's saying, fine, use this approach if you want, but just bear in mind it's not great, it's not perfect. Yes. And I think the same goes for all of those things. None of them are overly satisfactory.
And it's the same with circle theorems, it's the same with pi. It's all this stuff has the same issues. That's interesting.
So I agree with Ed on this in his book. He says basically beware. He's saying don't avoid these things. There's nothing wrong with them. I'm not convinced that they're a great use of the lesson time. I'd kind of rather, so there's our choice of demonstrations, and I think I'd rather just tell them. I'd rather just tell them, but then someone will say that I'm not giving them the full understanding, but I don't know. There's 180 degrees in a triangle. It's a fact.
Well, there's debate for the listeners, Joe. We like to be controversial.
I'm just not convinced about any of those.
Yeah, okay.
Anyway, so we can get them. Here's the rule that we want them to practice now, and we want them to really go into depth on practicing this rule. We're not going to do it in 5 minutes. We're going to spend a couple of lessons on this. The proof is going to come later.
Yes.
The reason the proof comes later is here's the proof, and the proof involves angles and parallel lines. They're alternate angles.
Yes. Now this is what I've used. Yes.
Now that's fine, but I'm not doing that in the beginning of year 7 because they haven't done their angles and parallel lines. So this was Ed Southall built this gift for me, and it's just your straightforward proof. There are other proofs. Yes. There are a couple of ways you can prove this, but this is the one that mostly gets shown to students. But don't show them when they haven't done parallel lines. Now, there's a number of worksheets and practice exercises we can do here. And if you look at this one, it seems pretty straightforward to start with.
Yeah, fine.
And it gets a little bit more interesting, And actually, there's an interesting fact here about the exterior angle being equal to the sum of the two interior.
Yeah, that's
There's some interesting stuff there that you can look at. But then this goes on to more interesting problems and questions where we're basically practicing angles and triangles throughout. This is Ed Southall's worksheet from solvemymaths.com. But there's a really nice set of questions. So here he's got 20 questions, all on angles and triangles.
Yes.
You do need to bring vertically opposite angles in for the last few.
Interesting decision with the labelling being separate to the diagram, right? Do you know what I mean? So question 14, theta, you've got to look in the box to see it's 40 degrees, not in the diagram. That is interesting.
But I suppose because the diagrams get a bit cluttered, maybe?
Possibly, yeah.
I don't know, that is interesting, yeah. Because I suppose if I'm doing these questions, I'm going to write them on the diagram. Yeah. This is, I believe, an old Key Stage 3 stats question.
I think I've seen this.
And actually look at the sort of, if we're doing a lesson on angles and triangles, there's a question to our students.
There's a bit of everything.
Yeah, because you need to do your right angle, you've got to do angle and triangles a
couple
of times.
I like it.
There's a white rose one. This is nice. So it's equilateral triangle, the big one, and then he's cut a corner off.
Yes.
And then we need to find x. So first of all, you have to realise that the top right corner is 60 because the original triangle is equilateral. But then you have to realise that the one next to 145 is still a linear pair, an adjacent angle on a straight line, just because it's been moved away a bit. I quite like that.
I like that.
Yeah. There's loads of nice questions on this. I mean, I could go on all day. The isosceles triangle questions, I love them. I love anything to do with isosceles triangles. I mean, look at question...
And just back on that one, Joe. Again, what's like question 3 is nice, and 5, the fact that the tilting around
the
a
orientation
little bit.
of the shapes. These are Don Stewart. Look at question 1 on that sheet. Not a single number given, but you can work out angle A. It's really nice. Yeah, I love things like that.
Yeah, that is good.
I mean, Don Stewart has a great set of isosceles questions. You could do a whole lesson on isosceles triangles very easily.
Yeah.
But yet people sort of mention it and then they move on.
Yeah.
You could do a whole lesson on it.
Yeah.
Look at this one. This is CIMT. You're given that OA is perpendicular to the base, and you're being asked to find A, B, and C. And you're only given that one angle there, 40, and it's just isosceles triangles, it's really nice. I mean, I'd happily do that.
Yeah.
And if you're gonna teach angles and triangles, you really can't move on. If your students can't do this, then there's nothing complicated in it. It's basic angles and triangles.
It's nice though. And this is all about going deep into this, so that whenever we do build upon this and like parallel lines and all that come into play, and even circle theorems, which rely a lot on isosceles triangles.
Yes, they do.
This needs to be automatic to kids, doesn't it? You don't want them thinking or not just not knowing this like this, but you don't want them having to think super hard about isosceles triangles whenever we're trying to do all the more
complicated stuff. It needs to be automatic, doesn't it?
Yeah.
Now, like I said, I could go on all day with beautiful resources here. This is from, do you remember a resource called Sumbooks?
Yes, I do. Yeah,
so these are higher Sumbooks. I use them for the first
couple
of years.
They're good, Sumbooks. I like
I've still
Sumbooks.
got them and I always forget to use them, but these are from, these are pretty tough. These are classic angle questions.
And these are all, again, for the benefit of listeners and viewers. You're going to link to all these are in the PowerPoint.
Yeah.
People can treat themselves to these. That bottom left looks a bit 3D, doesn't it?
It does. It's a funny question. Yeah. MathsPad has loads. I can't show all the MathsPad stuff here, but some of it is free, some of it's subscription. MathsPad has tons of lovely resources. Angle chases.
Angle chases are good.
The left one's white rose, but yeah, you can chase an angle.
Joe
around.
Morgan, question for you.
Yes.
Right? Let's say we're doing this angle chase.
Yes.
You're doing it with your kids.
Yeah.
How much are you insisting they write reasons, or are you just interested in the answers?
Oh,
God, this is okay.
I hate all that reason writing.
Oh, that's interesting. But of course they're going to need it.
Not in an angle chase, no.
But they're going to need it for the exam, right?
There'll be some questions, like say for example something like where that one I might ask for some reasons.
Yes.
Because there were a number of different steps and reasons, and there's actually not. There's maybe have to write down 3 or 4 things. An angle chase is meant to be fun, quick, race to the end. There's no way we're writing down reasons.
Because again, I mean, the reason I ask, there's 2 arguments, isn't there?
Yeah.
If we get the kids to practice doing the reasons, they can become more routine to them and then finding the exam. The flip side of that, as you say, is it can get in the way of mathematical thinking. It's annoying. Like you get a kid, I just want to crack on, I've got to write this flipping sentence.
That's all the fun out of that. Like,
interesting,
You remember I showed you a resource in parallel lines and I gave them a tick box thing where they could tick the reasons. Like, anything that I can get them out of writing reasons, I will.
That's interesting. I think I could split the crowd that, Joe. But anyway.
And then finally, and something we can do to stretch our students. So if you've got a really smart year 7, year 8 or any year group class and they're doing angles and triangles, then proof is how you stretch them. I mean, there's some really good proof questions. This is takes you through a basic proof. It says that if we know that those 2 angles are 60 and 105, how do we work out x? Give reasons.
Yes.
Now do the same for the next one, give reasons, and that's just different numbers. And now we've got a y and a z in there.
Yes.
So it's just building them up into that idea of how do we lead in, it's going to be the same idea as it was for the 2 numbers. That's scaffolding proof. And then you've got things like John Stewart, who has, these are proof questions. Prove that B equals 2A and stuff like that. Like this is really much more challenging than all the other.
But again, it's still isosceles triangles.
Yeah,
so that's
we're staying within. We're not trying to push them onto angles and parallel lines.
Exactly.
We're staying with angle basics, but we're doing secondary maths. We're doing stretching maths. We're using all the stuff we've taught them.
And this is the classic thing. They've met this in perhaps, year 5 or something, this isosceles, but we can still go deep without having to race through.
Yes, absolutely. So this is what we're aiming for. Like you said earlier, you can't. I mean, that's a hard circle theorems question.
Flipping heck. A bit of a jump.
I love circle theorems. You cannot do circle theorems without, like you say, a strong knowledge of isosceles triangles and just generally straight lines, vertically opposite, all your angle facts. You are lost on circle theorems without them. So we have an end point here. I mean, like I say, there's not much angle geometry at A level apart from trigonometry, but if we want our students to go on and achieve high grades at GCSE, they have to master the basics of angles in year 7 and 8, or they won't be able to access this stuff at all.
We can do circle theorems at some point, Colin. I flipping love a circle theorem.
What a great topic. There's some teachers that hate them. What's going on there?
I'm not friends with those. So there we have it. That was topics in depth angles, and which you may say, Joe, could supplement the topics in depth angles in parallel lines. Why wouldn't you say it? So, Joe Morgan, thank you very much.
Thank you, Craig.
And Tez, thank you so much for hosting. And for you, thank you so much for watching or listening. We'll be back with another topics in depth session in the near future. Bye for now.